Hello everyone, my name is Mengyuan Li. I'm from the Ohio State University. Today I'm going to present our paper, Exploiting Unprotected I/O Operation in AMD's Secure Encrypted Virtualization. This is a joint work with Dr. Zhiqiang Lin from OSU, Dr. Yansu Lin from University of Central Florida, and my advisor, Dr. Yingqian Zhang. Well, traditional cloud service will always face two problems. One problem is that hypervisor must enforce full isolation between co-residence clients. However, logical isolation using page table is usually not good enough. Sometimes it may break down, and there are so many very famous attacks like meltdown attack, Spectre attack. And another problem is that the cloud user must fully trust the cloud host. Because of this, many cloud users worry about hypervisors stealing their data and monitor their behaviors. So current cloud design is not ideal for both user side and cloud host side. Based on those concerns, AMD combines traditional cloud service with hardware memory encryption, and they put forward a new technology called Secure Encrypted Virtualization, SEV. Let's look at how SEV handles those problems. In AMD's system on chip, besides CPU, there is another processor called the secure processor, which will manage some AES keys and handle SEV APIs. There is another unit called memory controller, which will in charge of AES encryption and decryption. For software level, the hypervisor will still need to host the guest VMs, while at the same time, it needs to call different SEV APIs for VM management. There are also some slight changes in guest OS kernel to fit SEV environments, like choosing which memory region to be encrypted using its own guest page table. With the help of SEV, all data in random access memory is AES encrypted in default, and both hypervisor and guest VMs have their own and unique AES keys, and these keys will never be exposed to hypervisor or guest VM. More details: when data is stored in cache in CPU, those caches are tagged with their ID. Thus, both the guest VM or host cannot access others' cache line. In random access memory, data are encrypted with different keys. So when guest VM reads data from memory to cache, cache will be automatically decrypted by AES engine, and when guest try to write data to memory, data will be automatically encrypted. So both host and malicious VMs who try to access others' memory region will only get useless data because their keys are different. With SEV's design, it can protect different kinds of attacks, like some physical access attacks and some administrator access attacks. So SEV provides a way to isolate guest VM or container from malicious tenants, and it can also help protect the guest owner from malicious hypervisor, which is able to convince those customers their VM are safe in the cloud. Moreover, it is very convenient for guest owner to use SEV since there's no need to change their own software or existing code. There is an additional technique detail of SEV which is related to our work, that is the AES algorithm used by SEV. Because the memory is accessed randomly, SEV uses ECB mode and an additional physical address-based tweak function here. So when the AES engine encrypts the data will first be XORed with the tweak function. However, the tweak function can be easily reverse engineered according to the paper Secure Encrypted Virtualization is Unsecure in 2017. Okay, that's the end of the background, and let's begin to look at the problem in SEV's design. So when we look at the SEV's design, we find that SEV focuses on protecting memory. Even some previous attack towards SEV also only focus on how to break SEV's memory integrity. But when we look at guest VM's other components in cloud, like storage I/O, network I/O, or display I/O, we find that those components are under host's fully control, but there is no protection from hardware. So here comes the question. How do SEV handle I/O requests from guest VM, and are they secure enough? Let's first look at an example of a disk I/O read request from guest VM in SEV. The guest VM will first check its own page cache. If that file isn't in its memory yet, then this request will be handled by hypervisor use KVM and QEMU structure. Then the hypervisor will read the file from disk and store the data in its own page cache. However, data in host page cache cannot be directly used by guest VM because data is not encrypted by VM's AES key yet. To solve this problem, guest VM needs to use a structure called Software I/O Translation Buffer, SWIOTLB. The guest OS kernel will set the Software I/O Translation Buffer as unencrypted and reserve this memory region to transmit I/O data with hypervisor. With the help of Software I/O Translation Buffer, the hypervisor will put data into this area, and then guest OS kernel will perform a memory copy to copy I/O data to its own guest page cache. This is how SEV handle I/O requests from guest VM. We will then show that the current I/O design, the Software I/O Translation Buffer, is not secure in SEV environments, which may break the confidentiality and the integrity of SEV's trust model. We will show how Software I/O Translation Buffer may break the trust model when the I/O is not software encrypted or even when the I/O is under software encryption. We consider the attack here a privileged adversary like a malicious host who can control the KVM and the QEMU structure. So without software encryption, the malicious host can directly sniff and modify guest I/O data. Like here, for example, during boot period, when guest VM load SSH binary, the malicious host can sniff code segments of SSH binary and change some code before the binary is actually used by the guest. Like here, we only change 5 bytes data in SSH binary from E8, C2, BF, FD, FF to B8, 00000000. By doing so, the malicious host can bypass the authentication process and directly gain the control of SEV guest VM. This example is trying to show that if I/O doesn't have any software encryption, the malicious host can be rather powerful. However, even with software encryption, like SSL, TLS encryption, or full disk encryption, the SEV guest VM is still unsecure. We will show that even encrypted I/O can produce decryption and the encryption oracle. We will first talk about the attack scenario. The OpenSSH is a common software in Cloud VM and is widely used by cloud clients to control their VMs. All transmission between guest owner and VM is software encrypted, so it is really safe. We will then show how hypervisor may make use of SSH packets to build a decryption oracle and an encryption oracle, and thus break the memory encryption. Let's first talk about the decryption oracle. The decryption oracle can be further divided into 3 steps. The first step is pattern matching, the second step is ciphertext replacement, and the third step is packet recovery. The attack steps. So because the SSH handshake protocol is performed in plaintext, the attacker who controls the hypervisor can act as a man-in-the-middle attack and recognize the established SS channel by its IP address and TCP port number. Once the secure channel is established, there will be frequent packet interaction between guest VM and the guest owner. Every character guest owner types will produce a SSH packet, and a corresponding acknowledged packet. So here, hypervisor targets all SSH packets, and when hypervisor senses there are some incoming SSH packets from guest owner, it will clean all present bits in the nested page table in order to produce a fine-grained page fault side channel. The fine-grained page fault side channel is based on two-level page table structure in SEV. As shown in the figure, even all guest's memory is encrypted as well as guest page table. The hypervisor is still in charge of managing nested page tables, which will transfer guest physical address to the real system physical address. Thus, if hypervisor clean present bits in the nested page table, when guest VM access a memory page again, there will be a page fault, and the page fault will need to be handled by hypervisor via a VM exit. At the same time, this VM exit will leak many information, such as the guest physical address the VM want to access, the page fault error code, like it is a write operation or read operation. By recording and analyzing those page fault sequence, the corresponding time, the hypervisor can somehow learn guest VM's behavior. So after receiving the incoming SSH packet, the guest VM will send an acknowledged packet back to the guest owner. Internally in the guest VM, when SSH tries to send that packet, the encrypted data is first copied to the buffer of the transport layer, then the buffer of the network layer, and then the buffer of the data link layer. In each layer, new packet headers are added. Eventually, the entire network packet is stored in a data structure called SK buffer. Then the kernel will call a function to transfer the data in SK buffer to the device driver, where we call it period buffer, BP. The goal here in step 1 pattern matching is to locate period buffer use fine-grained page fault side channel. So after locating the period buffer, the attacker will replace the header of the outgoing SSH packets with the secret the attacker wants to decrypt. Let's look at the detail of a SSH packet and why attacks are able to replace the header with the secret. As shown in the figure, the header of a SSH packet contains many metadata like destination address, source address, the network port, tags, or flags, which will always remain the same in the lifetime of a SSH connection. So for one SSH acknowledged packet, which is usually around 90 bytes, 32 bytes of metadata can be predicted and can be temporarily modified by attack, and the attack is also able to recover those data later. Let's go back to the attack steps. So after the attack replaced the header of the packet, then because of the setting of software I/O translation buffer, the guest VM will do a memory copy from period buffer to the shared buffer, and the attacker is able to directly read the block in software I/O translation buffer and get the plain text of the secret using the tweak function. After that, the attacker will recover the packet with correct header and forward those packets to client owner. The whole process is efficient and can be done without notice of both guest VM and guest owner. Let's look at some performance data. For the pattern matching performance, the training and testing VM are different VMs with the same Ubuntu version. The average precision is about 96% and the average recall is around 85%. And according to our experiment, the period buffer will remain unchanged and reused for multiple network packets. This greatly helped the attack, either by performing pattern matching once and reusing the same period buffer directly in subsequent packets, or by improving the accuracy of the guesses. We record 5,000 SSH packets with rates ranging from 0.5 to 20 packets per second and collect over 200 different period buffers. In the experiment, 56 period buffers are reused more than 100 times and 95% period buffers are reused more than 10 times. This table shows the performance of an end-to-end attack in decrypting a memory page of 4096 bytes. In 10 PPS setting, when use 2 blocks to do the decryption, it will only take around 18 seconds to decrypt a 4096 byte memory page. Well, then the encryption oracle. The encryption oracle is a very similar but reverse process. For detail of the encryption oracle, please refer to our paper for more details. Okay, the discussion. First, we want to talk about the solutions to unprotected I/O operations in SEV. There is some hardware solution like authenticated encryption, which we will talk more detail in the paper. But here, we want to talk more about the software solution. To temporarily fix the problem, all I/O operations, including network I/O, disk I/O, and or display I/O, must be forwarded to a trust server that is controlled by the VM owner. And all transmission need to be encrypted with transport key, which is only known to the guest owner and the AMD secure processor. Second, we want to talk about the physical address-based tweak function. According to our contact with SEV team, they are planning to use an advanced tweak function in the next release. However, because of the software I/O translation buffer, there will always be many pairs of plaintext and ciphertext during the lifetime of a guest VM. Whether we can reverse engineering the new tweak function or make use of it is still unknown. The third, we want to talk about SEV and SEV encrypted state, which is a more secure version of SEV. In SEV-ES white paper, it will mask some information during VM access. But because SEV-ES is not published yet, we have done some experiments in pattern matching to find the pattern without some information, which may be masked, like the offset, the page fault error code. And we only use sequential page frame number, the size, to build a course green the page fault side channel. The result shows the average precision is still 90% and the average recall is around 70%. Firstly, we want to talk about hardware encryption supported DMA. For Intel CPU, there will be a similar technology called total memory encryption and multi-key total memory encryption. In their white paper, the DMA will also be supported by hardware encryption with different keys. This may produce a way to solve the I/O problems in SEV. However, there's no such feature for AMD CPUs yet. Here comes the conclusion. It is the first exploration of unprotected I/O operation in SEV, and we show example of encryption and decryption oracle caused by unprotected I/O operations. And we proposed both hardware and software countermeasures. And more importantly, we want to make SEV clients aware of SEV's limitation, which may help them make better use of SEV. Thanks for your listening. If you have some questions, feel free to contact me with the email. Thank you.
Any questions?
Questions are, I'll go ahead and ask one. This showed how to do the Oracle with network packets. How would it work? Would it be different with disk I/O, or is it just application dependent?
In theory, it's the same thing, but we just do not do this experiment. But in theory, as long as the operation, they are all vulnerable to this type of attack.
Okay, and the key step is being able to do a true man in the middle where you can fake the second half.
Well, I would say, well, the key step is to identify the buffer, the encrypted buffer in the guest VM, and then replace the content of that buffer. That's the key step, right?
Hi, Jan Michalewski from Mengyuan. Thank you for the talk. Quick question about the tweakable cipher. So you mentioned kind of some concerns around being able to reverse engineer the tweak. The tweak function is usually completely known. So what are exactly the concerns around that, and what's the threat?
Sorry, I did not hear you.
So the tweakable ciphers, the tweak function is usually known. There's no need to hide the function itself. What exactly are the concerns there?
Okay, so about tweak function. If the tweak function is known, that means that the attacker is able to reconstruct, will find a correlation between the ciphertext and the plain text very easily, because the tweak function actually the tweak function takes the input as a physical address, right? If the attacker knows the target physical address, the attacker is able to reconstruct the target ciphertext. But in the new design, I believe AMD will try to hide the tweak function so that the attacker is not able to guess the tweak function to reconstruct the ciphertext at a specific location. I think this is the goal of the AMD's new design, but I do not know the exact design detail, and I cannot say whether this is secure or not. But this is one of the countermeasures against this attack by hiding the tweak function.
Thanks.
Okay.
All right, let's thank our speaker.